right. So before we get to the question here, a lot of times my wife likes to draw pictures of people. She's a pretty good artist, and a picture that she drew of a person that was just yesterday, it looked pretty good, but I told her the eyebrows were a little high, and I don't know, she just seemed surprised. Happy Friday, everybody. Hey, what did the monster say after he got done eating the boat? Yeah. What's that? Water? Good guess. I can't believe I ate the whole thing. Because hull is a part of a boat. All right, it's Friday indeed. Okay. I can't believe I ate the whole thing. Because a hull, H-U-L-L, that's a part of a boat. I know this is the one part of your day you look forward to in the morning. Okay. Why do many runners prefer to land midfoot as opposed to on their heels? Any guesses on this one? It's kind of an interesting one. So we're going to talk about this. And the only way to really talk about it is to just kind of get a close-up view of it. So, if you're running... thank you. If you're running and you land... How's it going, Max? On your heel... What's automatically happening if you're trying to go this way?
Going that way.
Thank you. Yeah, if you're going on your heel, and this isn't being picked up by the camera. Let me just quick fall off the table here. But if you're landing on your heel like that, then you automatically have like a force going backwards against you. Because when you land, all that force is going back up your leg, and you have sort of a net force in reverse. So a lot of people like to land more straight up and down because then that force goes straight up instead of back. You don't automatically have that force going backwards on you when you run. This actually makes a big difference, especially for distance running. I noticed when I ran competitively a few years ago, I started by just running like a normal person. You run, and because you've got a heel that's usually about an inch higher than the front of your shoe, your foot just kind of naturally lands on its heel. And that's actually not good if you're trying to make a good time, whether it's sprinting or whether it's distance running. So, like if you're sprinting, nobody's going to land on their heels because of that force. Once you start landing on the balls of your feet or midfoot, you're going to get much better times, both in sprinting and in long distance. And the best way to do that is actually not so much to try and consciously, land straight up and down. The best way to do that is to actually increase the rate at which you are stepping. So from what I remember, I think 180 steps per minute is kind of the ideal frequency that you're going to hit the ground. And I really wanted to hit that. So they actually make songs that you can buy on like iTunes and everything, specifically at those beats per minute, so you can, step and run along with it, and try and get that good, they call it a gait, get that ideal gait in your running frequency. So, I know that's kind of a long answer, but the short way to put it would just be, when you land on your heels, you've automatically got a force backwards. When you land on your heels, you've automatically got a backward force. Backward forces are not good when you're trying to run forward.
I just thought it was because if you were running in seconds,
yeah, that's true. That's true. The other thing you can do that I noticed made a big difference for my running too is if you get racing flats, because then the heel isn't raised. And if the heel isn't raised, then you kind of have a more natural motion to your run. Like, remember when you were kids and maybe you ran around on the grass in your bare feet? You don't naturally land on your heels when you do that. Your body's more designed for you to land midfoot. And when you have a shoe that has a bigger heel in the back, it kind of encourages you to run in a way that you weren't really designed to. So if you have racing flats with no heel, that'll automatically make your running form a lot better too. But the biggest difference I noticed, if this matters to anybody, if you're in track or anything, was to try and increase my number of steps per minute to 180. Once I did that, I got really, really good times. So, okay, let's take a look at worksheet number 4. So, worksheet number 4, number 1. This is going to look a lot like all those other questions that we've done. So let's take a quick look at it here. So we've got the boxes. One is on the flat surface, one is hanging off with the string. If the coefficient of friction is 0.2, what is the acceleration of the block? So we got to go through the same 4-step procedure that we've gone through in the past for this kind of a problem. The only difference is we have a friction to take into account. So we've got a 4 kilogram mass, we've got a 1 kilogram mass. I don't think I need to do the force diagram. You guys know these by now. For the 4 kilogram mass, you've got gravity down, normal force up, you've got a tension going to the right, and you've got friction going to the left. In terms of the 1 kilogram mass, it's got tension up and gravity down. So for the force equation, we have to do a force equation for each object in the direction of its motion. So for the 4 kilogram mass, it is moving horizontally. So we have to do a horizontal force equation. So that's going to be tension to the right minus friction to the left is equal to ma. And I put a little subscript 4 next to that so I don't forget this is the 4 kilogram mass. For the 1 kilogram mass, it is the hanging mass. And its force equation in the direction of its motion is vertical, so we got to take tension, force, and gravity into account. What is that force equation going to be? Fg minus Ft? Don't we usually go up minus down? You are right. Yeah, exactly. Because that hanging mass is going to be going down. So gravity's winning this battle. Therefore, gravity must go first in the force equation for block 1. So there we go. So we're halfway done with our procedure. We did the force diagram, kind of virtually. And these are the force equations. Step 3 is to isolate your tension force in both of these. So force of friction, I'm going to shift to the right to keep the tension force by itself. So that'll be ma. And when I move this over, it becomes positive. And remember, force of friction is coefficient of friction times normal force. On this side, I'm going to move tension over here, and that makes it positive. And I'm going to move this product over to the left, and it makes that negative. Force of gravity is mg. And when I move this over, that becomes negative. And that's all equal to tension force. So, the final step in all of this is both this and this are equal to tension force, so we can set those two things equal to each other. So let's do that and plug in those numbers. Mass is 4. Acceleration is a. Coefficient of friction is 0.2. Normal force on a flat surface with nothing pulling up or pushing down is just equal to mg. So that's going to be times 4 times 9.8. So this thing here, these three numbers, is coefficient of friction times normal force. And now I set this equal to that. M1 is mass 1, the 1 kilogram. G is 9.8 minus 1 times A. So now we just get the A's on the same side and move the numbers to the other side. So this would be 5A over here. So I got this being 7.84. So it's going to be 9.8 minus 7.84. It's going to be 1.96. That's going to be on the right side here, because I take this and I move it over there, making it negative. So 9.8 minus that is equal to 1.96. So to solve for acceleration then, I just divide both sides by 5. And when I do that, I get an acceleration of 0.392. meters per second squared. And that's number 1A. Questions on that one? Okay, so letter B then says, what is the minimum coefficient of static friction required for no motion to occur? Now it's the same setup. So it's the same force diagrams, the same force equations. The only difference is now there's just no motion. And if there's no motion, this is going to change a little bit. What changes is that, I think I'll just kind of back up a little bit. What changes about these two things if there's no motion is the acceleration is equal to 0. So now my force of friction, which is mu times normal force, is going to be equal to m1g. And then we can just plug those numbers in. Thanks. So coefficient of static friction is what this would be. And I'll just isolate here right away. So divide both sides by normal force. And in this case, again, normal force is just mg. Now, the part that I saw some folks messing this part up is, you might think, well, these cancel, and then that's just equal to 1. But you got to remember, we're dealing with two different masses here. So this is the 1 kilogram mass. This is the 4 kilogram mass. So the g's will cancel. But 1 divided by 4 is just 0.25. So your coefficient of static friction is 0.25 for letter B then. Questions on that one? Okay. Next up, number 2. I saw a lot of folks have some trouble with number 2. So we'll go through this one together. If you're still writing that, feel free to keep going. Again, for all these problems, start with a force diagram, do a force equation, and then you can solve. And number 2 is no different. Number 2 says, a 300 Newton block is moved at a constant speed over a flat surface by a 50 Newton horizontal applied force. So, if I was doing a force diagram, I would have gravity down And I just realized we're getting near the end of this chapter. This might be one of the last force diagrams we ever do. Isn't this sad?
That means there's a test.
Yeah, it does.
So,
Wait, what's next chapter?
Projectile motion. And that's a fun chapter because it brings everything that we've learned in like the last 2 months all together. Yeah, it's the chapter where you throw stuff. We actually, one of the examples, we checked to see how far you could actually land if you ran straight off the roof of Martin Luther. More specifically, would you actually land on the sidewalk part, or would you make it into the parking lot if you were at top speed? So that's kind of an interesting thing to think about. Look forward to that. Okay.
do we go on the roof?
No, we don't.
Wait, so none of us are running off of the roof?
No.
Oh,
No. I mean, that would be... We'd need mattresses. But if we could get them, I would love to do that.
Or like one of those big inflatable, like, you know what I mean, where they catch people.
Yeah, we could rent one of those inflatable castles. Just like on The Office. You guys remember that episode? She was going to jump off the roof into the inflatable
You
castle.
probably should tell Mr. Compton.
No, he'd never go for that. This is going to be a physics thing. This is for science.
First hour physics only.
First hour, yeah. I have a feeling if we did it, that we would only do it this hour. Okay, so this is our setup. And one of the most important things about this problem is that it's moving at a constant speed. So if it's moving at a constant speed, what that means is these two forces are equal. So if it was speeding up or slowing down, they wouldn't be. But because we're moving at this constant speed, the applied force and the force of friction are going to be the same value. So when it says, what is the coefficient of friction? I'm going to start by setting up my force equation. And because we have ourselves a situation where we have no change in velocity, acceleration is 0, therefore applied force equals force of friction, and applied force is given to us. Force of friction is coefficient of friction times normal force, and normal force in this case is just going to be equal to mg, and it says directly here it's a 300 Newton block. So if it's a 300 Newton block, that's exactly what mg is. So 50 divided by 300 is equal to coefficient of friction, which ends up being equal to 0.167.
Is it okay if I put 3.17 and then like the repeating sign?
That's okay. So that's 2b. 2c, what would the block's acceleration be if there were no friction? Well, if there were no friction, it is indeed going to accelerate, and our force equation would change a little bit because the acceleration's not 0 anymore. In addition to that, we also no longer have friction, so it goes away. So it's just applied force equals mass times acceleration. So if the applied force is given as 50, and that's equal to mass times acceleration, bless you. And if I want to solve for acceleration, oh no, I'm not given the mass. What can I do to find the mass here?
Divided by 9.8.
Exactly. So it gives us force of gravity. That's the 300 newtons. So if I want to get the mass, I got to go 300 newtons divided by 9.8, and that gives us a mass of 30.6. So to solve for acceleration, you divide both sides by 30.6, and you'll get 1.63. And that's the front side. Take that front side. I can't believe we did the hull front side.
Wow.
You guys owe me more chuckles than that.
No, we really don't.
Yes, you really do. You are in debt. Doesn't count.
Will you give me a on this next test?
I will if you get a 92% or higher. Okay. So number 3. A 100 Newton force is applied to a 50 kilogram crate resting on a floor. The coefficient of friction is 0.15. Draw a force diagram for the situation. So this is just like the force diagram for the last one. You've got an applied force to the right. You've got friction to the left. Gravity down, normal force up. So what is the acceleration of the crate? No surprise here. We got to do a force equation for the direction of the object's motion. So acceleration is just equal to applied force minus friction over the mass. So we've got all those numbers, and we just got to plug them in. Applied force is 100. Force of friction is coefficient of friction times normal force. And in this case, normal force is just mg. And the mass is 50. G is 9.8. Any questions on where any of these 3 numbers came from or why I'm doing this? This force of friction is just mu times normal force. So there's mu. Normal force is mg. And we divide that all by the mass, which is 50. And you get an answer of 0.53.
When we do that, should we round to the nearest 100?
That would be fine.
Okay. That's
That's okay. All right, number 4. I touched on number 4 briefly when I handed this out to you a day or two ago. So it says, in the situation described above, which is this one, the coefficient of static friction is 0.25. Will the 100 Newton force cause the crate to accelerate? Draw a force diagram and explain. So, we got to figure out if 100 newtons is enough to make this accelerate if our force of static friction is 0.25. So, what is not changing over this whole scenario from part A to part B is this 100 Newton applied force. That stays constant. So all we got to do is we got to figure out if our 100 Newton applied force is bigger or smaller than the force of friction. So let's just see what the new force of friction is going to be, and then we can figure this out. So force of friction is coefficient of friction times mg. And what does that come to? Can somebody tell me? All right, 122.5, all this down to 123. So 123 newtons is the force of static friction. In other words, if we have a force that is pushing on this object that is less than 123 newtons, it's not going to go anywhere. So, is this block going anywhere? No. It's stuck in place. The applied force is not big enough to overcome the force of static friction. And that's number 4. On to the last one, number 5. Oh good, an incline problem. So we've got a 20-degree incline there. And we've got a 10-kilogram mass that's sitting on it. What is the value of the force of friction opposing the block's slide down the ramp? Now, if you took the notes that I gave you a couple days ago on this, remember that anytime you're on an incline, your force of friction will always be equal to mu mg cosine theta. Always, always, always. That's what it comes down to if you calculate your normal force, and your normal force would come to this with that angle, and there's your coefficient of friction. So this is just coefficient of friction. This long mess over here is the normal force. So we can just directly plug the numbers in. And as long as your calculator is in degree mode, you're going to get 13.8. And that's letter A. So let's do letter B. Unfortunately, for letter B, we really got to do a force diagram here. Otherwise, it's going to be a little bit too abstract. So in letter B, we're looking for the acceleration of the block. So, figure out the acceleration of the block. We got to know what all the forces are. So there's our force diagram. And of course, because we're sitting on an incline, we got to take our x and y axes and we got to rotate them. In this case, we'll be rotating them a little bit clockwise. There's our new x-axis, our new y-axis. So this force of gravity is acting in two directions. It is both acting in the x direction and it is acting in the y direction. So now we have at least a good starting place here. So my force equation then for letter B is going to be all the forces pulling the object down the ramp minus all the forces trying to stop it from going down the ramp. So that's going to be FGX minus friction equals ma. So, obviously, we calculated the force of friction already. We know the mass. We're looking for acceleration. The only other thing we need to find in order to get acceleration is this force of gravity in the x direction. So, priority one is to calculate that guy. So, it's right here. And in order to figure this out, we need a couple things. We need an angle, and we need a hypotenuse to this triangle. So, I'm just going to make my angle here. So the little wedge is on the right side. So if I took that angle and slid it in somewhere without twisting it or turning it, it would slide right in here. So that's 20 degrees. 70, 20, 70, and that's as far as we really need to go. Force of gravity, we know the mass is 10, so that means force of gravity is 10 times 9.8. 10 times 9.8 is 98, so it is the hypotenuse of this triangle. So now I just want to try and figure out what the adjacent side of this triangle is, and that's what FGX will be equal to. So, this is the adjacent side of the triangle, so I'm going to be using cosine, and that's equal to adjacent over hypotenuse So FGX is going to be equal to 98 times the cosine of 70. And when you do all that, you get 1.97. Nope, never mind. I'm going to have to calculate it out. 1.97 is the actual answer. $33.5. So that's your force of gravity in the x direction. So 33.5 goes in here. Force of friction we found to be 13.8. That goes in here. Mass is 10. So then we got to solve for acceleration. And when you do that, then, to get a by itself, divide both sides by 10. So that'll be this right here. And when you do that, you should get 1.97. All right. Final questions on worksheet number 4. Okay, I'm going to come around and grab those from you then.